Imagine this. You've got a massive list of items, and you need to keep them perfectly sorted. But you also need to be able to find, add, or get rid of any single one of them in a flash. It sounds kind of impossible, right? Well, that's the exact promise of a really cool data structure called a binary search tree.
I mean, think about it. This is a huge problem in computer science. If you just have a simple list, searching through it is painfully slow. If you have a sorted array, adding something in the middle means shifting everything over. We need something that gives us the best of both worlds.
And here's the answer. The binary search tree, or BSD for short. Now, the entire thing, the whole shebang, is built on one beautifully simple rule. For any item in the tree, we'll call it a node, everything to its left is smaller and everything to its right is larger. That's it. Seriously, that one rule is the key to absolutely everything.
So here's our game plan for this explainer. We're going to really dig into that one simple rule. Then we'll look at searching and inserting, which are super intuitive. We'll tackle the 3 cases for deletion. That's the tricky part. Then we'll get into performance, the good and the bad. And finally, we'll see why BSTs are still such a big deal. All right, first up, let's talk about that one simple rule and how it really does define everything about this structure. So check this out. Here's something really cool that just falls out of that rule. If you walk through the tree in a specific way, visiting the left child, then the node itself, then the right child, and you just keep doing that, you will read out every single item in perfect sorted order. It's not some extra process you have to run. It's just baked right into the structure itself. How cool is that? Okay, let's move on and see how this one rule makes the most common operations a total breeze. We're talking about searching for an item and inserting a new one. Searching is so intuitive. You just start at the very top of the tree, at the root. And at every single step, you just ask one simple question. Is the number I'm looking for smaller or larger than the one I'm currently on? If it's smaller, you go left. If it's larger, you go right. You just keep following that path down until you either find what you're looking for or you hit a dead end, which just means it's not in the tree. Simple.
And inserting a new number? Get this. It's pretty much the exact same logic. You pretend you're searching for the key you want to insert. You follow the same path, left for smaller, right for larger, and when you hit an empty spot where it should be, boom, you just attach your new node right there. And what if the key's already there? Well, a common trick is to just add a little counter to the node that's already there, so you don't even have to change the tree shape.
So, searching and inserting? Piece of cake. Deletion, though? That's where things get a little more interesting. But don't worry, it's not as bad as it sounds. We can break it down into 3 simple cases. Basically, any node you want to get rid of is going to fall into one of these 3 buckets. Either it has no kids, it has just 1 kid, or it has 2 kids. Now, the first 2 are super easy, but that third case, that one requires a clever little trick to make sure we don't break our one simple rule. Okay, so cases 1 and 2 are no sweat. If the node is a leaf, with no children hanging off of it, you just snip it off. Done. If it has only 1 child, you basically just play matchmaker. The node's parent now points directly to its grandchild, completely bypassing the node we wanted to delete. We've spliced it out of the chain, and the sorted order is totally fine. But the real puzzle, the one that makes you think for a sec, is case 3. What on earth do you do when the node has 2 children, a whole left side and a whole right side? You can't just remove it. The whole thing would fall apart. The solution is this really elegant algorithm called Hubbard deletion, which was figured out way back in 1962. So here's the magic trick. You don't actually delete the node you're targeting. Instead, you find its replacement. This replacement is called the in-order successor, which is just a fancy way of saying the very next biggest item in the whole tree. How do you find it? Easy. You take 1 step to the right, and then you go as far left as you possibly can. Then you copy that successor's value and paste it right over the node you wanted to delete. Finally, you just delete the original successor from its old spot. And what's great is that is now a super simple case 1 or case 2 deletion. It's so clever. The structure holds and our sorting rule is perfectly preserved.
All right, now for the million-dollar question. Performance. We said these things are fast, but there's a catch. A really big catch that every single developer needs to know about.
I mean, it seems like just following a path down a tree should always be pretty quick, right? Well, not so fast.
And this slide tells the whole story. The speed of a BST depends entirely on its shape. A balanced, bushy-looking tree is great. It's short and wide, so the paths from the top to the bottom are really short. But an unbalanced, skinny tree, that's a disaster. It's tall and stringy, basically just one long, sad path. And this table gives us the hard numbers. In the average case, with a nice bushy tree, operations take what we call logarithmic time, or theta of log n. That is incredibly fast. It means you can double the amount of data, and it only adds like one extra step to your search. But in the worst case, it degrades to linear time, or theta of n. That means doubling the data doubles the search time, which makes it just as slow as a boring old list.
So how do you end up with that terrible, slow, skinny tree? It's painfully simple. You just insert data that's already sorted. Think about it. Each new item is larger than the last, so it always gets added to the right, and then the next one goes to the right of that, and so on. Your beautiful tree turns into a long, pathetic stick, and all those amazing speed advantages, poof, gone. Okay, so you might be thinking, well, with this huge potential downside, why do we even bother with BSTs? It all comes down to choosing the right tool for the right job. Let's put it head-to-head with another popular kid on the block, the hash table. Now, hash tables are often even faster for just looking up one thing. They have an average time of O of 1, or constant time, which means it takes the same amount of time no matter how much data you have. But, and this is the huge trade-off, it gives you absolutely no sense of order. You can't ask a hash table to give you everything sorted or to find all the items between X and Y. So, when should you reach for a BST? Here's your checklist. You use one when you need that order. If you need to list out all your items from smallest to largest, or you need to find the absolute smallest or absolute biggest value in a snap, or you need to do range queries, find all the keys between 50 and 100, a BST is the perfect choice. It's built for exactly these kinds of jobs. And this quote just nails it. A plain, simple BST is wonderful to implement and understand, but it gives you zero guarantees against that worst-case skinny stick scenario. If you absolutely positively need that super fast logarithmic performance every single time, you have to level up to a more advanced self-balancing tree. Which leaves us with one final, really important question. We love the power of a BST and its ability to handle ordered data, but that worst-case performance is a real risk. So how do we get the guaranteed speed of a balanced tree and the beautiful simplicity of the BST's core rule? How can we make sure our tree never becomes a slow, skinny stick? Well, the answer lies in something called self-balancing trees, and that's a story for another explainer.